Today I want to talk about the LC filters. That means capacitor and inductor used to make a filter. Now, specifically I'm going to be talking about the first and second order filters. For the reason what it means, first order, number of, or second order, or whatever order of the filter is, just refers to the number of actual components used in the filter, and the stiffness of the filter, and how big is the attenuation of the filter. Okay, or what is the what is the attenuation of the actual filter? So basically you get very many different filters. I'm going to talk specifically about the Butterworth first and second order filter. The reason why Butterworth, because it is the most usable sort of filter in the industry, and most likely that you will encounter it somewhere if you're in the electronic environment, some kind of a Butterworth filter. Now you do get many different types of filters. I'm just going to sort of show you, and I'm showing over here, 4 basic filters. You get the low pass filter, which consists of the inductor, capacitor, and you can see actually from 0 lets a signal through at FC, the cutoff frequency minus 3 dB starts attenuating, and all the signal over here is basically not fully attenuated, but as I said, it's definitely attenuated. Then you get the high pass filter, which consists of the capacitor and the inductor. Of course, that's our input, that's our output of the filter. And that is called the high pass filter. Now, high pass filter, you can see over here, it's not passing anything below the cutoff frequency. And where it's minus 3, it starts actually passing. So from here onwards, it will pass all the frequencies. And below the FC, it will attenuate them. Okay, now it depends what attenuation according to the order of the filter and according to what type of is it a Bessel or is it a Butterworth or whatever other sort of type of a filter. Then of course we do get the band pass, again, or input or output, and they call it a shunt filter, which are connected between the wherever or input and or negative, positive and negative. Okay, it's just connected across in parallel. And of course, you will get the resonant frequency where the signal is the strongest, and then you will get the FC cutoff, lower cutoff, and then you get the FC higher cutoff, which all the frequencies will be sort of attenuated below this before and below this FC, the cutoff point. And of course, we do get it's called a band stop, or they call it a notch filter, as they say, notch filter. Okay, now very usable filter, and I've got one practical. Anyway, we got our positive, we got negative, positive, negative. That's our out. Okay, and it consists of coil and capacitor. And this is a typical first order, they call it, filter. Now, with this very simple filter and calculating proper sort of values of the L and C, inductance and capacitance, I can achieve whatever frequency I want and attenuate it. And I will demonstrate just now on the actual instrument. If you see over here, I will demonstrate this particular board, and you can actually see it in real time, the actual notch that I've drawn over here, okay. Now this is a typical, I just took a piece of scrap, a PC board, I soldered for convenience and quick sort of demo, fitted a BNC female and a BNC male. And then of course over here I'm going to feed the signal from my portable generator, sweeping with this particular plug. I'm just going to connect it up over there, and this will go into the spectrum analyzer, and then we'll be able to actually see the response on the spectrum analyzer, display something which is very much alike like this with the center frequency, which we can precisely read on the instrument. So now if you look at it over here, center of BNC, I just put a straight wire. It looks very clumsy or whatever, but it's just for a demo purposes, and it does work. It's not so critical. As I said, it's a low frequency. And I'm going to try to attenuate a radio amateur band, which is 145 to 146 megahertz sort of frequency. And we will display it, and you will see it. And we will see exact attenuation of the filter, which consists of the inductor, which is this one over here. Okay, I don't know if you can really see it. Okay, and the capacitor, which is put across, as I said, this is ground of this one and this one here. They're joined via the copper, and then the centers are joined with this wire. And then I got basically in series inductor with the capacitor soldered down to ground. So on that note, yeah, let me just connect it up, and then you'll see what I'm talking about. Okay, let me connect the generator. I'll just screw it in, and then let me just get my camera. Okay, and then I will put it in. Let me just do this. Okay. The wire came off, but nonetheless, that is the ground. I will connect it up, and basically, you can actually see. Okay, if you look at it very carefully, now any filter will have multiple sort of harmonics and so on, where it actually attenuates. But nonetheless, we are interested at 145. Let me just adjust it. I'll just bring the camera a bit closer so you can actually see it. Now, if you look at it very carefully, over here, it's 143, 145. Okay. Now, this is the center line. Okay. And this one, the marker, let me just shift it a bit away. It is right in the center of 145. Now, between this marker and that particular marker, let me just set it properly. Just a bit lower. There we go. Okay, let me just do this. Okay, so it's basically, from the center line to the center line. Okay, so from there to here, if you look at it, it's attenuation of the actual filter, this specific filter, that inductor and the capacitor as a notch filter is basically, if you look at it over there, 27. I can quite comfortably say, in practical ways, call it 25 dB attenuation. From that particular point to that particular point, somewhere over there, okay? Now, I can, of course, zoom onto it as much as I like, and of course, I would have to move the markers once I zoom in, type of thing. But nonetheless, it is, if you look at it over there, it's 145. That's where it is, 145. And that's basically what the notch filter is, and it corresponds 100% with this picture. In other words, it lets the signal go through at 145, which is a cutoff frequency, attenuates my signal by about 25 dB. And then as we increase the frequency, it starts letting it go through. Now, the bandwidth of the filter is measured at -3 dB. And this specific filter, the way I designed it, it will operate from about 130, -3 dB. Lower point is about -3 dB. -3 dB is at approximately 130 megahertz. And higher sort of cutoff point where the signal starts going through, which is minus 3 dB, is at approximately 160 megahertz, with the center frequency of 145 and maximum attenuation. And that's what actually I require. So I can connect it up across my antenna system or across the FM antenna or any other electronic circuit where the radio amateur 145 sort of megahertz is interfering. So yeah, that's in a nutshell basically what it's all about. Very simple circuit, as I said, consists of the inductor and a capacitor across the sort of positive and negative of the input signal, and that's our output. And over here, say for example, wherever the signal strength is, over here is minus, it's attenuated at that specific frequency at 145 minus 25 dB, which sort of approximates to about 700 to 800 times attenuation. So this signal is about 700 to 800 times smaller than the input signal here, which in most cases it will do quite a miracles top out in most of the cases. But as I said, if you want more attenuation, sort of deeper or even more narrower sort of, then you have to go for higher order filter, which would include second, third, fourth, fifth, whatever order. And that will increase the number of coils and capacitors, sort of the actual filter and complexity of the filter. But in most of the cases, first order filter for the notch filter, 25 dB, good enough. On that note, on the notch filter, I say thank you for watching, and until next time, with maybe a low pass filter explanations and so on. Thank you.